Okay, give me 10 minutes and I'm going to get you through electricity jargon. A lot of people get reasonably good at electricity and know how to use formulas and get questions right and so forth, but they fail to understand what exactly it is that they're calculating and measuring and so forth, because a lot of the definitions of how electricity gets measured are a little bit garbled. So I'm going to have a go at it here. I'm going to try and simplify this. All right, I've drawn a fat wire. This is a wire, right, with some electrons that we can magically see going that way, right, leaving their little trails of smoke behind them. Right? That's my way of showing that they're moving. I know, beautiful artistry, thank you. So how does this get measured? Well, the first quantity you need to understand is current. Right? Current is literally how many electrons are going past per second. Right? So it's a bit like somebody's put a person here, counting them as they're going past 11, 12, okay? Now, because there are so many electrons in reality, there aren't 5, there are loads, we don't count them in electrons. Otherwise, the numbers would be just too big for anyone to understand, right? We'd be quoting current as 4.7 by 10 to the 26 electrons or something. And they're numbers that people just don't get. So we've, like scientists always do, we've found an easier way to do it. We've picked a very big number and called it 1 of something else. We've called it 1 Coulomb. Now, 1 Coulomb is 6.25 by 10 to the 18 electrons, right? It's an enormous number. It's a million, etc. You don't really ever have to know that number. I had to look it up, and I'm a physics teacher, right? I don't remember it in my head. It's a bit like doing chemistry and knowing that a mole is 6.02 by 10 to the 23, and then hardly ever using that number again. You just speak of things in moles, right? We're just going to speak of things in coulombs. So current is literally measuring how many electrons go past in 1 second, right? So 1 amp of current is 1 coulomb, that many electrons going past a point in a wire in 1 second. That's all it is, right? So this wire down here, which has got heavier traffic, right? More electrons, greater electron density, but they're going at about the same speed. You'd imagine if this guy was looking down here and counting the electrons going past, that would have about twice as much current because it's got about double the electrons going at the same speed, and you'd be right. So current is literally how much traffic density there is inside the wire. Voltage is something a little bit different. Let's have a look at this. Current is how many electrons there are going past. Voltage is how much energy they're carrying. Right. So here's 2 wires here. Both got the same electron density, the same number of electrons moving past a certain point, but some of them, this is my way of drawing a more energetic electron, right? Looks like it's going faster. Thank you for the thank you for the compliment on my artistry again. So this would have a low voltage because these guys don't have as much energy as these. This would have a high voltage. They'd have about the same current. Because these are going faster, there might be a few more electrons going past in a second, but the current isn't going to be 3 times as much as that, or twice as much, or 5 times as much. It'll be pretty similar, right? So current is how many electrons are going past in a second, and voltage is how much energy each coulomb of electrons has. Once again, it's per coulomb, it's just per big bundle of electrons for convenience. All right. Now this is all related to energy because that's what we use electricity for. It's a form of energy. And sorry about that. And because this is more relevant per second rather than as a total, we tend to be talking about power rather than energy. Power is how much energy something can use or create in 1 second. It's the rate of energy use or the rate of energy creation, right? Now, obviously, if we stood here all day counting the energy going past here, we'd get an enormous amount, but that's not particularly relevant. What we really want to know is how much energy is going past per unit of time. How quickly can we use it? Right? So voltage is directly related to power. Right? Voltage is how much energy each coulomb goes past, and of course, current is how many coulombs are going past in 1 second. It's always per time. So voltage is directly related to how much power is available, and so is current. Obviously, it makes sense that there must be twice as much power coming through this wire as through there. If all of the electrons have got an equal amount of energy and twice as many are going past per second here, this has got double the power, and that's dead right. And it also makes complete sense that if we've got the same current here, but these guys are carrying more energy each, if these guys are carrying twice as much energy each as those, then this is developing twice as much power. And again, that's correct. Power is directly proportional to voltage, and it's directly proportional to current. So, having seen all that, I'm going to show you your best friends' formulas. Current first. Now, there are other formulas with current in it, and there are other formulas with voltage in it, but these are the definitions. These are the definitive formulas, right? Current is how much charge is going past in a certain amount of time. It's coulombs per second. Q stands for charge, right? The amount of charge going past, the amount of moving electrons in this case, right? And it's in coulombs per second, as I said. And if you can't remember what it's in, by the way, what the units are, the formula tells you that's coulombs, that's seconds. So it must be coulombs per second, right? You can use a formula to figure out the units of something. And you can also go the other way. You can use the units of something to figure out what the formula must be. It's got to be the coulombs divided by the seconds, right? Now, in deference to a guy called Ampere, who did part of the discovery of electricity a couple of hundred years ago, we've renamed coulombs per second and we just call it amps or amperes. Okay, voltage. And again, there are other formulas with voltage in it. This is the definitive one. This is the one that defines voltage. Voltage, like I said, is the amount of energy each coulomb of charge is carrying. It's joules per coulomb. And sure enough, there's the units. And again, we've renamed this. Instead of joules per coulomb, again, in deference to somebody who helped invent electricity and figure it all out, we've named it volts after Alessandro Volta. Power. Power. Now, this here is the general form of power. Now, power doesn't just come from electricity, it comes from a lot of different circumstances, but in every case, it's the amount of energy something provides each second. So that's the general form of the power formula. The specific one for electricity is voltage times current. Like we said before, it's directly related to voltage, it's directly related to current. So this makes sense that both of those would be in the formula, and it would be a direct proportion relationship. And it's measured in watts. And finally, energy. Again, there are other formulas for it, but this is the definitive one. Again, this is the general form, right? Energy is power times time, right? It's literally a rejig of this. I've juggled that formula around to get this. Same deal. They're intimately related. The specific one for electrical energy is this. Again, power times time, right? And it's in joules. There you go, my friends. That is electricity jargon 101.